Think about the last time you watched someone walk down a street. It is a seamless motion. The weight shifts from one foot to the other. The arms swing to balance the momentum. It looks effortless. Now imagine trying to replicate that exact motion with a machine. You might expect a robot to look just as fluid. But in reality, current prototypes often stumble. They hesitate. They look mechanical. This is not just a matter of programming the joints correctly. It is a fundamental conflict between the physics of heat and the timing of signals. Here is the reality of thermal management and robotic locomotion. Every time an actuator moves a leg, it generates heat. In a human body, blood flow and sweat manage this temperature naturally. In a robot, that heat has nowhere to go. If the system gets too hot, the electronics can fail or the materials can warp. This is why many prototypes struggle with sustained movement. They are designed for short bursts of activity rather than the endurance required for a human walk. The engineering challenge is not just making the leg move, but keeping the engine of that movement cool enough to function reliably. Now consider the issue of latency. When a robot decides to step, there is a delay between the command and the action. In a complex environment, that delay can be catastrophic. If the floor is uneven, the robot needs to adjust its balance in milliseconds. If the signal takes too long to process, the adjustment comes too late. This is where the bottleneck becomes critical. We are not just fighting gravity, we are fighting the speed of information processing. The faster the robot moves, the more sensitive it becomes to any lag in the system. This brings us to a surprising finding from recent research. Scientists have discovered that the most efficient walking mechanisms can be achieved with extreme simplicity. There is a bipedal robot known as Mugatu that demonstrates this principle. It uses only one actuator and two rigid bodies to achieve stable, autonomous walking. This challenges the assumption that we need complex control systems to mimic human locomotion. By stripping away the unnecessary components, the robot reduces the sources of heat and latency. It proves that mechanical simplicity can sometimes outperform mechanical complexity. However, there is another side to this equation. While mechanical efficiency is vital, it is not enough for public integration. We see this clearly in video analysis of airport cleaning robots. These machines are technically proficient. They can navigate a terminal without crashing into walls. Yet, they frequently disrupt social order. They fail to understand human motives. They do not grasp group dynamics. When a group of people is walking together, the robot treats them as a single obstacle rather than a coordinated unit. This causes friction. It creates a sense of unease in the public space. The core problem here is a lack of interactional competence. Current designs treat movement as a purely technical function. They prioritize collision avoidance over social alignment. A robot might successfully avoid hitting you, but it might do so in a way that feels aggressive or unnatural. This is because the algorithms focus on geometry rather than intent. They calculate paths based on distance, not on the shared understanding of how humans move together. This creates a divergence in the field. On one hand, we have academic research focusing on minimalistic, energy-efficient walking principles like the Mugatu design. On the other hand, we have industry trends attempting to replicate complex human anatomy. There is a growing question about whether mimicking human gait is the optimal path for general-purpose utility. If a robot can walk efficiently with one motor, why do we build it with 20? The answer lies in the social context. For a robot to work in a human environment, it must be perceived as safe and predictable. Recent studies suggest that the perception of human-like walking is so advanced in some systems that it triggers skepticism. If a robot looks too much like a human but moves slightly wrong, it falls into the uncanny valley. This indicates a threshold where mechanical smoothness rivals human dexterity in public perception. We need to find the sweet spot where the robot is efficient enough to be practical but social enough to be accepted. Future research must address how to imbue these efficient, specialized robots with the nuanced understanding required to navigate human spaces collaboratively. We need to move beyond simple collision avoidance to true social alignment. This means integrating complex social navigation algorithms into minimalist or specialized mechanical platforms without compromising their core advantages. It requires a shift from viewing movement as a technical function to viewing it as a collaborative accomplishment. We see this in the potential of wire-driven quadrupeds as well. These designs offer a resilient alternative for harsh environments by eliminating onboard electronics. They are robust against dust and heat, but to be useful in public spaces, they too need to understand the social rules of the road. They need to know when to yield, how to pass, and how to respect personal space. The primary knowledge gap lies in bridging these domains. How do we integrate complex social navigation algorithms into minimalist or specialized mechanical platforms without compromising their core advantages? While mechanical designs are advancing toward compactness and resilience, the lack of interactional competence remains a barrier to seamless public integration. We are building the body, but we are still learning the language. Ultimately, the path to human-level walking is not just about better motors or faster processors. It is about understanding the context in which that walking happens. It is about recognizing that a robot in a transit space is not just a machine moving through a void. It is a participant in a shared environment. It must understand that a person waiting at a gate is different from a person walking through a corridor. It must understand that a group of friends is different from a line of commuters. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.